Hi, everyone. So, the next two lectures, we're going to be looking at climate change. Now, this is a huge topic, right? It's of great importance, and really, we could be devoting an entire course just to it. But what I'm going to try and do in these two lectures are highlight the main points. So, you come away from this knowing what climate change is, what's causing it currently, what are its impacts, and what we can do about it. So, in this first lecture, we're going to be looking at the drivers of climate change, both the historic and current. So, we're going to start by defining what climate is, right? We should have an understanding if we're talking about climate change, what exactly is changing. We're then going to look at the paleoclimate, or essentially the history of the climate on Earth, right? The history of the Earth's climate. And we're going to look at what we know about it, right? What was the Earth's climate in the deep past, and how do we know that information, right? It's not like we were out there 1,000 years ago, 100,000 years ago, a million years ago, with thermometers measuring. So, how do we know what the temperature in particular was way back in the Earth's history? From there, we're going to look at what were the drivers of climate change in the past. As we're going to see, the climate is not stable. Throughout the history of the Earth, it has never been stable, right? It changes over different time periods. So, what were these drivers in the past, right, before humans? And then we're going to shift and we're going to look at our current climate. And we're going to talk about the role that the atmosphere plays in warming the Earth. We're going to talk about greenhouse gases and how they affect global warming. And then we're going to talk about the anthropogenic drivers of climate change. And anthropogenic just means really human or human caused in this instance, right? Because what we're going to see when we get to the current climate is that our current change is largely due to increases in greenhouse gas emissions from us. So to start, we're going to define climate, right? Now, there is no standard definition when we are talking about climate, and really, definitions can be grouped into two categories. Either they are weather focused or they're systems focused, right? So, a weather focused definition of climate is essentially what you probably all think of when you are thinking of climate, right? It is the aggregate or the average weather conditions over a long period. Now, the World Meteorological Organization um, sets that period of about 30 years, right? So their definition would be the average weather conditions over a 30-year period, right? And that's kind of what we think of. I think most people think of that when they think of climate. But there's also a broader definition or broader groupings of definitions that are system focused, right? And in these definitions, we define the climate system as this complex interactive system that consists of our atmosphere, so the gases around the Earth, the hydrosphere, water, cryosphere, where that water's frozen, right? The poles in our case, the lithosphere, so the outer shell of the planet, so like geology, and the biosphere, right? So as we're going to see, what determines what we may think of as the weather-focused climate, right? What determines the Earth's temperature and precipitation, drought conditions, etc., is this complex climate system of all these interacting factors. So this definition then would be our climate would be the state of that climate system. So the state of all these interacting factors. And this is the definition that the Intergovernmental Panel on Climate Change has adopted. And we're going to talk about the IPCC in the next lecture when we look at the impacts of climate change and projections and what we can do about it. Right, so it's two definitions of climate, just something to be aware of. So if we go back in the Earth's history, what do we know about the paleoclimate, right? So the ancient climate of the Earth. Well, we don't have systematic measurements of the Earth's temperature before 1880, right? At 1880 is when we really started getting or gathering data about the Earth's temperature from various locations on the Earth, right? So at that point, we started getting more accurate data on what the Earth's temperature was. So if we want information prior to that, we have to use temperature proxies. And a proxy is essentially any sort of measurement that can then be calculated to a value of temperature, right? So we're using something different, and from that measurement, we're able to estimate what we think temperature was. And we have different temperature proxies, right? If we're not going too deep in time, we can use old documents, right? Even though we weren't measuring temperature before 1880, we did have earlier or closer to that time period, there were different measurements of temperature that were going on. If we go back in further into human history, there are records of weather patterns and temperatures, etc., that we can look at. But besides that, we have three other really important temperature proxies. They are tree rings, or dendroclimatology, ice cores, and ocean sediments. And we're going to look at each of these three in the next couple slides. So dendroclimatology is looking at tree rings. And the things you need to know for this is that trees grow one ring a year, right? And importantly, the growth of a tree, or a growth of plants in general, is affected by temperature. So plants will grow more during warmer temperatures, as long as they have sufficient moisture. So if you look at the size of a tree ring, larger sizes will indicate warmer temperatures, right? Because they're growing more, they're going to grow more in those warmer temperatures. So if you have a larger ring, generally that year was warmer. So by looking at the size of these tree rings, scientists can get an estimate of temperatures in the past. Right, so right here we could see this example, right, of this cross section. We could see those tree rings. What do you think would be the warmest years out of 1 through 9? Right, they are going to be those years where we have the largest tree rings, 5 and 7. And our coldest year is going to be the one actually in between there, 6, right, where we have that shortest tree ring. Right, so this is one way that scientists are able to estimate temperatures in the past, as well as precipitation. Right, and in fact, there was a recent paper that came out that used this methodology to trace the past 1,200 years in the American West and Southwest, looking at the temperature and drought conditions there. Right, so it's an effective way to look at the Earth's climate in the past. Now, if we need to go a little bit deeper into the past, we can utilize ice cores, right? They can provide us information going further back in history. Now, ice cores are essentially what you think of, right? They're that picture that you see down there. They are cores of ice that are drilled in various locations on the Earth, particularly at the poles. And these ice cores are able to trace back hundreds of thousands of years, particularly those in Antarctica, right? We have very good ice cores that give us a history of the past 800,000 years. There's actually a recent one that may give us a record all the way back to about 2.7 million years ago. So we have really good information going back using these ice cores. And if we go to the Arctic region, right, so the North Pole area, we have ice cores that we take there that don't go as far back, but still can trace back to about 130 years before present, right? So these ice cores allow us to get information on the Earth's climate going back almost a million years, with that recent one potentially 2.7 million years ago. So how does that actually work? Well, we can look at the thickness of the different ice layers in that core, right? And they will tell us information about precipitation, right? Thicker layers would have been more precipitation. There are air bubbles that are trapped in the ice, and we can analyze those air bubbles to get an idea of the ancient atmosphere. And then importantly, we can calculate temperature from the proportion of different oxygen isotopes. Now, I'm not going to go too deep into this, but I just want to touch on it because it's an important method that we use for the ice cores, as well as the next metric that we're going to look at, or the next method that we're going to look at. So oxygen can have multiple isotopes. The most common one is O16, where there's 8 protons and 8 neutrons in the nucleus of that oxygen atom. But there can also be O18, which has 2 extra neutrons. And looking at the proportion of the O16 to O18 will give us an idea of what the temperature was at that time period. So how that works is O18 is going to be naturally heavier than O16, right? It has those 2 extra neutrons. So when this oxygen is bound up with hydrogen in water, the water that's going to evaporate first is going to be the O16 water, right? Because it's lighter. That O16 has 2 less neutrons. It's lighter than the O18. So during cold periods, that O16 water evaporates into the atmosphere, and then eventually it's going to precipitate back down onto land. Eventually, right? It's going to make its way onto land. Well, during cold periods, when it falls on that land, it may be falling on ice, right? Or maybe forming ice when it falls. And when that happens, it no longer is going to flow back into the ocean. So if we are drilling for an ice core and we have a lot of O16, it's at this particular time period, it's going to mean that our temperatures were colder during this time period, right? Because that O16 water was evaporating, it was falling on the land, and it was getting locked up in the ice that was on the land. So the temperatures must have been cold. And the opposite is true during these warm periods, right? That O16 is evaporating, it's falling onto the land, but now it's melting or running back into the ocean. So we'll have a less amount of O16 water in our ice during these warmer periods, right? Does that make a little bit of sense? You don't really need to know the specifics of this. I just kind of wanted to highlight it for you because it is a really important way that we are able to determine temperatures. And we've done these studies and we've compared it to known temperatures that we have, recent temperatures that we have actual measurements for, and in that way we're able to dial this in to get really good estimates of ancient Earth's temperatures. If you want a little bit more information on this, there's a really good video here that you guys can Google and watch on YouTube that will explain this in a little bit more detail. But essentially what you need to know is that the proportion of this O16 to O18 is able to tell scientists or give them an estimate of what the temperature was during different periods when they are looking at these ice cores. And then our last proxy that we use is ocean sediments, and this lets us go back even further, right? Those ice cores let us go back about 1 million years, potentially almost 3 million years. But our ocean sediments let us go back in history all the way to about 540 million years ago, which is right around, I think that's the Cambrian period, when really multicellular life started developing. And this process uses the exact same process as we just saw with the ice cores, right? It's evaluating those oxygen isotopes. In this case, it's evaluating the oxygen isotopes that are incorporated into the shells of marine fossils. Right, so there are these marine organisms called Foraminifera, which are these single-celled organisms, and they incorporate oxygen into their shells in the form of calcium carbonate. Well, it's the same idea. In this case where there is a warm period, there's going to be more of this O16 rich water coming in, right, because it's not getting trapped in the land ice. So they'll have more of this O16 in their shells. During cold periods, they'll have less of it, right? So by looking at these isotopes and by evaluating the proportion of O16 to O18 in the shells of these marine fossils, we're able to get estimates of temperature all the way back as far as 450 million years ago, which is pretty amazing. Those are the Foraminifera right there, right? Very, very tiny, single-celled. So, given these temperature proxies, what does it tell us about the temperature on the Earth through history, right? Well, if we look back using those ice cores and we go back about 800,000 years, we see this pattern on the top here, right? This is, here is temperature right here. And we see this pretty regular cyclical pattern of warm temperatures and cold temperatures, and warm temperatures again and cold temperatures occurring about every 100,000 years, right? We're seeing this pattern. And this is what we refer to, these cold periods are ice ages, right? This is a cyclical pattern of ice ages during these cold periods and interglacial periods right here where things get warmer. And then you have another ice age and another interglacial period, another ice age, another interglacial, etc., all the way to present time, where we're at the end of our interglacial period. We should be going back to another ice age. However, we're going to see we're not doing that. And down here are carbon dioxide concentrations, and you see they match up pretty closely, right? This is some of the evidence for the warming effect of carbon dioxide, as we'll talk about a little bit later. But these cycles were discovered, or at least popularized. I guess he discovered it or gave the reason why this was occurring by Milankovitch, and they're referred to as Milankovitch cycles. He was a Serbian mathematician. And essentially, what he hypothesized that was causing this cycling of an ice age and interglacial period was the orbit, tilt, and wobble of our planet over time. So our planet varies in those things, right? If you look at the orbit of our planet, it varies over a period of about 100,000 years. That matches up really well with our ice ages. It varies from being more circular to being more elliptical over that period of 100,000 years. Its tilt also changes over a period of around 41,000 years, right? So the actual tilt of the Earth changes over this short degree or a range of degrees, and its wobble also changes slightly, right, over a period of 19,000, 23,000 years. So all of these things in combination, this orbit, tilt, and wobble, affect the distribution and thus intensity of sunlight around the world. And this is really important because as we affect the intensity of sunlight, think of it, sunlight is energy and energy produces heat, right? Energy is turned into heat. So as we're affecting the intensity of sunlight, we're affecting the heat that a certain area is receiving. And this is going to affect global warming or global cooling. But it's not just the intensity, right? If it was just the intensity of sunlight, it wouldn't have the great effect that we see, that going from this nice interglacial period to an ice age. There has to be more to it. And that more to it are these feedback cycles that happen, and particularly feedback cycles related to carbon dioxide. So what's happening during a warming period is that we have that wobble and tilt of the Earth, and it's affecting the intensity of sunlight, particularly in the intensity that's falling on our poles, right? The Arctic and the Antarctic. And that's increasing the energy that these areas are receiving, and it's increasing the heat. Now, that's going to lead to slightly warmer ocean temperatures. And when this happens, it reduces CO2 solubility, right? So you can think of it like when your soda gets warm, it gets flat, right? There's not as much bubbles in it, right? The same thing is happening with the ocean, right? When the ocean gets warmer, it can't hold as much carbon dioxide. And as a result, some of that carbon dioxide gets released from the oceans and into the atmosphere. And then once it's in the atmosphere, it has a greenhouse effect, which we're going to look at in a couple slides later, which that greenhouse effect further increases the heat of the area and further warms ocean temperatures. And this cycle continues. And this positive feedback cycle continues between carbon dioxide and now warmer oceans, resulting eventually into this nice interglacial period that we find ourselves in right now, right? Going from an ice age to this warm period. And this is only possible with this CO2 feedback cycle. It wouldn't happen just due to the orbit, the changing in the orbit or the tilt of the sun. So this is really, really important. Now, that can go the opposite way too, right? That's the warming way to lead us to this interglacial, but it can also go the opposite way and can lead to cooling, right? So our tilts or orbit changes of our sun, that's going to affect the intensity. In this case, it's lowering the intensity that our poles are receiving or that the Earth is receiving in certain areas. That leads to colder ocean temperatures. Now, when the oceans are colder, they can hold more CO2, so they absorb more CO2 from the atmosphere. This lowers atmospheric CO2 concentrations, and now we have the opposite at work right here, right? And it leads to this cooling, and it eventually leads to an ice age. So these are these Milankovitch cycles that we see, and they match up really well with CO2 concentrations. And this was calculated, like I said, by Milankovitch back in 1912 by hand. He did these thousands of calculations to show these cycles at work, right? So that's one of the ways that one of the drivers of historic climate change, particularly these Milankovitch cycles that we observed over the past 800,000 years, are due to that orbit and tilt of our Earth and the feedback with carbon dioxide. Now, if we go back a little further in history, we see we kind of get out of those cycles, right? So this is what we're talking about with those Milankovitch cycles right here. Now we're looking at 65 million years ago, right? Here's the end of the dinosaurs or non-avian dinosaurs. This is right afterwards. Earth was much hotter at that time period. We may be going back to that, by the way. So the Earth was much hotter, and then we had these periods of glaciation and thawing and reglaciation. And we think a big driver, or at least another driver of this besides CO2, is ice and albedo feedback, right? So again, we have this feedback cycle, right? And in this case, a big driver was this change in albedo. So albedo is the ability of a surface to reflect sunlight and essentially reflecting heat, right? So ice has very high albedo. It's able to reflect a lot of sunlight and thus reflect a lot of heat. So if we reduce ice, right, we are reducing the ability to reflect that energy, and instead it's going to lead to warming. So again, this is another feedback cycle that worked along with that CO2 feedback cycle, right? So we have some sort of external forcing, right? Changes in our orbit or tilt or wobble of the Earth. That's going to lead to warmer ocean temperatures, right? This is the warming cycle. Because of those warmer ocean temperatures, we have the retreat of polar ice caps, right? And this is related again to CO2, right? And this is all multiple feedback things happening at once. So we have the retreat of polar ice caps. Because of that, we have a decrease in global albedo, right? That ice was really good at reflecting energy. Now we don't have that. So now the Earth is absorbing more energy and more radiation is absorbed to the surface. That leads to warmer temperatures and this cycle continues, right? And the exact opposite would be for cooling, right? We'd have colder ocean temperatures, an increase of ice caps, increase of albedo, less radiation, and et cetera, right? So you could see how it goes one way and the other. So that's another feedback cycle that is important, or was an important driver of climate change in the Earth's history. And now we can go even further back, and this is using those fossil records that I talked about from those marine sediments. And this is essentially a great history of temperature on the Earth, right? And you can see, here we are, present day, very, very tiny. You can't even see that. This is where we were looking at in the last slide there, that about 65 million years ago. And now we're looking all the way back to about 542 million years ago. And you could see, right, over this long time period, there is this variability that has occurred in the Earth's climate, right? From particularly warm areas, much warmer than we have nowadays, to cooler periods, to warmer periods, cooler, and vice versa, right? And then we've had these glacial periods and interglacial periods, etc. So over this long time span, those other processes are at work, right? Those CO2 feedback cycle, albedo cycle, but there are other things happening as well. And we think some of these large scale effects or large scale changes that we see in here is due to the movement of the continents or the tectonic plates and how that affected ocean circulation, right? So over the Earth's history, we know that the tectonic plates have shifted, right? And that has shifted our continents. And while that has happened, when that has happened, it has affected ocean circulation. Now, ocean circulation is a key regulator of climate. We saw in our feedback cycles, right? It was one of the first steps, right? Warmer ocean temperatures, colder ocean temperatures. It is a huge regulator of climate, not only for those feedback cycles, it brings warmth to certain areas and vice versa. And when that is shifted or when that is affected, it can lead to these large scale changes or these big changes that we see in climate. So we do think some of those larger changes that we see over really deep time in the Earth's history are related to these changes in essentially the movement of the continents and how that affected our ocean circulation. So with that, we have three kind of big drivers of the changing climate in the Earth's past, right? We've had the wobble and tilt and change in orbit of the Earth's sun that increases the intensity of sunlight that falls particularly on the polar regions, which in turn results in these feedback loops, right? That involve carbon dioxide and albedo that affect there are two big drivers of changes in the Earth's climate. And then we have these changes and movement of the continents that result in shifting ocean circulation that affect global temperatures in the past. And there are some other things as well. Volcanoes and volcanic activity also have played a role in global climate temperatures. But in general, these are some of those big historic drivers of climate change. If you want more information on this, I would encourage you guys to Google. There's a lot of resources. There are lectures online. I utilized a lot of slides and information from the link that I have down here that talks about the paleoclimate. So I encourage you to watch that as well if you want to go deeper into some of this. But really, this was just to give you an idea of some of these historic drivers of climate change, and they're still at work in present day, right? That now that leads us to our current climate, right? We've looked at the paleoclimate, so the history of the climate on Earth. What about our current climate? Well, we've already mentioned CO2, right, and the greenhouse effect that it has. And I want to delve a little bit deeper into that because what essentially I'm proposing in this lecture, and essentially what the entire scientific community is proposing, is that our current climate change, our current global warming, is due to our emissions of greenhouse gases and how that is affecting our atmosphere. So to understand the greenhouse effect, we can look at, and to get some evidence of it, we can look at satellite measurements of energy, right, taken from space, right? So what's happening? Solar radiation is impacting the Earth, right? So energy from the sun is impacting the Earth, and it heats up the Earth, and then that Earth emits radiation, particularly infrared radiation, out into space. And what we've done is we can measure this outgoing radiation, and we can measure it, and it's about 240 watts per meter squared. And we can change that into a temperature, and that temperature is equivalent to about negative 18.7 degrees Celsius or negative 65.7 degrees Fahrenheit. So that is the measure of the outgoing radiation. But if we look at the actual temperature of the Earth, right, the temperature or average global temperature is about 14.7 degrees Celsius or 58.5 degrees Fahrenheit. So they don't match, right? So that difference between them of about 33 degrees Celsius or 92 degrees Fahrenheit, that difference right there is the greenhouse effect, right? Without the atmosphere, our global temperature would be synonymous or equal to what that outgoing radiation was, right? 240 watts or negative 18.7 degrees Celsius. But because of the effects of the atmosphere and the heating effects of the atmosphere, it's raising the average global temperature and essentially allowing us to live on the Earth. So what exactly is happening is this right here. It's kind of what I just talked about. We have incoming solar radiation. Some of that gets reflected by the ozone layer that we talked about, right? Cloud cover, etc. Some of it gets absorbed, but a portion of it passes through and gets absorbed by the Earth, right? And it creates heat, and then the Earth is going to radiate outward infrared radiation. So that infrared radiation gets radiated out from the Earth. Some of it gets through our atmosphere and goes out into space. That's what we're measuring right there. But a portion of it gets blocked by clouds and greenhouse gases and gets re-radiated or back radiated back down into the Earth. So the Earth is getting radiation not only from the sun, but infrared radiation that is coming back from these greenhouse gases, right? And that is causing the Earth to be warmer than it would be without the atmosphere. And this was postulated all the way back in 1824 by Jean-Baptiste Fourier, right? He calculated that the Earth should be a lot colder than it is, and he reasoned that the atmosphere must absorb some infrared radiation and radiate it back, right? And it took, this was done back in the 60s, so it took almost 100 years to actually get real evidence of that effect. So if we are talking about the greenhouse effect and greenhouse gases, right, that are absorbing this infrared radiation and re-emitting it back down to the Earth, what are these greenhouse gases? Well, again, there is a history of these greenhouse gases, of people discovering them, right? So way back in 1856, Eunice Foote, who was a female scientist, demonstrated the heating effect of carbon dioxide and suggested that it may be responsible for historic climate variations, right? So already back in 1856, she's identifying carbon dioxide as a potential greenhouse gas. And a couple of years later, John Tyndall, I'm not sure how to pronounce his last name, he proved and measured that water vapor, carbon dioxide, and nitrous oxide strongly absorbed infrared radiation, right? Adding more evidence to this. And in 1896, Svante Arrhenius, he's Swedish, I have no idea how to say his name, he published a paper suggesting that doubling CO2 would lead to a global temperature increase of 4 to 6 degrees. So this idea of climate change, of greenhouse gases, it's not new, right? This was, if you look at the newspaper article that I've included in the slide, that's from 1902, where Svante is talking about global warming and the effect of burning coal, burning fossil fuels, raising carbon dioxide levels, leading to global warming, right? All the way back in as early as the early 1900s, this was being talked about, or at least proposed by people, right? It's much older than you think. And I should note that this idea of greenhouse gases and them trapping and re-radiating infrared radiation, there is no debate on it. It is not controversial. It is accepted by everyone that this happens, right? So moving to modern day, right? What are the greenhouse gases and what do we know about them, right? Well, interestingly, one of the strongest greenhouse gases, or the strongest greenhouse gas, is water vapor, right? It absorbs the most energy. It has the largest concentration compared to the other ones. So it is the strongest greenhouse gas, but it doesn't have this large effect, and that is because it is regulated by the climate system, right? So when water vapor gets into the atmosphere, we think of that as humidity, right? It will trap radiation, lead to warmer temperatures, more water vapor, but eventually you get to a saturation point, and what happens? It rains, right? Or there's some precipitation. And then that water vapor is gone from the atmosphere. So really, a buildup of water vapor will really only last for about 2 weeks at max, before it's going to get rained out. So in this way, there's never this cumulative impact of water vapor because it's always being regulated. Once it gets too much, it rains, and then it's back in as water in various locations, right? So while it's strong, it doesn't have this long impact. So we often don't include it when we are talking about greenhouse gases, right? Because it's self-regulating. So the gases that we do talk about are carbon dioxide, methane, nitrous oxide, and fluorinated gases, right? So many of these, carbon dioxide and nitrous oxide, were talked about, as, like I said, back in early 1850s or late 1850s. So carbon dioxide, as you're probably aware, comes from the burning of fossil fuels, coal, oil, natural gas, and burning of wood and waste, and it's also produced in certain industrial processes. Methane comes from the extraction, handling, and transportation of these fossil fuels, right? So when they are excavating for coal, there are also often methane pockets surrounding that coal, that when they excavate for it, that methane gets released. Same when they are drilling for oil, methane is a portion of natural gas. So it gets released when they are transporting natural gas through leaks, or even the burning of these, the methane gets released. And methane also gets released with livestock production, right? When cows are burping, when they are farting, they are releasing methane, right? And that is a contributor to this percentage of greenhouse gases that get emitted, or methane that gets emitted. Nitrous oxide. Now, this is different from the nitrogen oxides that we looked at in air pollution, right? Those were NO, so one nitrogen atom, one oxygen atom, or NO2, one nitrogen atom, two oxygen atoms. This is N2O, right? Excuse me, two nitrogen atoms, one oxygen atom. So it's slightly different. And the biggest emitter or industry, I'm not sure if that's the right word, of nitrous oxide, it comes from agriculture, and really the application of nitrogen fertilizers. So post World War II, with the invention of synthetic fertilizers and synthetic nitrogen fertilizers, there was a huge increase in fertilization of our farm fields, and we've changed the way we farmed. I think I would argue for the worse, although there were very good short-term benefits. However, that increase in nitrogen fertilizer, that nitrogen gets absorbed by the soil. Soil microbes break it down to release nitrous oxide, and we have this release of nitrous oxide into the atmosphere that acts as a greenhouse gas. And then fluorinated gases. Those are CFCs, those chlorofluorocarbons that we talked about in air pollution, right? Luckily, through that Montreal Protocol, we have done a great job of reducing them. But there are still some other fluorinated gases, hydrochlorofluorocarbons, and some others that get produced and emitted through various industrial processes, right? So these are our main greenhouse gases, and you see them up here. And you could see that we're looking at the radiative forcing, and essentially what this is telling us is the effect of each of these on trapping heat, right, or creating more energy, or warming effect we can talk about, right? So you can see that carbon dioxide has the greatest warming effect out of all of them, and that is largely due to the amount of carbon dioxide there is compared to these other ones. There's another way of looking at this as global warming potential, or GWP. You might see that sometimes. And if you look at the GWP of these, it's actually methane and nitrous oxide are higher than carbon dioxide. Like methane is about 28 times, has a 28 times global warming potential, 28 to 26. Nitrous oxide is close to 300 compared to carbon dioxide. Some of these fluorinated gases can be in the 10,000s comparatively, right? So potentially they're able to trap more heat and emit more heat, but they're just, the quantities of them aren't as great as carbon dioxide, which is why it has such a large effect. And you can see here that the changes in these greenhouse gases, there's been a huge increase since the industrial age, right? It's around 1850 is that start of that industrial age. It's really when we ramped up industry, we ramped up the burning of fossil fuels, and as a result, we've seen this giant increase in the emissions of carbon dioxide, methane, and nitrous oxide, and as a result, a greater proportion of them in the atmosphere. And as a result, we are seeing climate change, or indications of climate change, or impacts of climate change, as we'll see in the next lecture, right? So we have this ramping up of these greenhouse gases. Now we're starting to see effects of climate change, right? And what are these effects that we're looking at, or these indicators? Well, we're seeing increases in temperature over land, right? Since 1900, that average temperature has increased by about 1 degree Celsius, which may not seem a lot, but when we look at, in the next lecture, future impacts, that any sort of degree is can have drastic impacts. I think I read somewhere that during the last ice age, it was only 4 degrees Celsius colder than it is now, and that led to having a mile thick layer of ice over top of New York City, right? So that's just 4 degrees difference. We've already gained a degree here, so it can have drastic differences. So we've seen increased temperatures. We've seen increased humidity, right? It's warmer temperatures, more evaporation of water, more water vapor in the atmosphere at any given time. We're seeing air temperatures are warmer, right? Not just temperature over the land, but temperature in the atmosphere. Increases in sea level, increases in sea surface temperature, temperature over the oceans, ocean heat content. All of these, decrease in snow cover, decrease in glacier mass and sea ice mass. All of these things that we would associate or would predict would happen with a changing climate or an increase in global temperature is happening, right? And it's happening right now. So what is causing it, right? What is causing this current change? Is it related to those Milankovitch cycles that we talked about, or is the orbit of the Earth? Is it something with the albedo, or changing or shifting of continents? And the answer to that is no, right? What is causing this current change in our climate is directly related to our emissions of greenhouse gases, right? Particularly carbon dioxide, as well as those other ones, right? And there are a couple lines of evidence to suggest this, right? The first is, if we look at those Milankovitch cycles, so over the past 800,000 years, we can see that our carbon dioxide levels never got above 280 parts per million and never below 180 parts per million, right? So for this past 800,000 years, That was the level of carbon dioxide through this whole time. Now we're at 400 parts per million, a huge increase. And this increase is coinciding with that industrial revolution when we started emitting these greenhouse gases, right? So we are way above anywhere we've been over the past 800,000 years. We can also see another line of evidence is this abrupt reversal in Arctic temperatures. So if we go back to here, right, if we're looking at temperatures and we're looking at these glacial periods and interglacial periods, we are actually on par to be going back towards colder temperatures, right? We should be, over this long 100,000 years, progressing towards another ice age if we were following these Milankovitch cycles. And really, up until about the Industrial Revolution, that was occurring. If we looked at our Arctic temperatures, we saw that they were decreasing. And then there's this abrupt switch that occurs right when we started emitting all these greenhouse gases. And we see now this increase in Arctic temperatures that we weren't seeing over the past 1,000 years or so, right? So again, this is a switch from what is predicted by these cycles, what we would expect if this was natural, right? Another line of evidence that this is being caused by humans and our emissions of carbon dioxide. Another line of evidence is this change in CO2 lag, right? This is sometimes used as to argue against carbon dioxide as a driver of climate change by some people. So if you look at these records right here, if we look at the ice cores and CO2 concentrations, we see, if we look closely at them, we see that there is a lag between carbon dioxide and temperature. So temperature peaks, and then about 800 years later, the carbon dioxide peaks, or the amount of carbon dioxide peaks. And this lag is due to this natural feedback process, right? What's driving this change in temperature, at least initially, is not the carbon dioxide. It is those external factors that we talked about. The orbit, the changing orbit of the Earth that is affecting the amount of solar radiation that's impacting our ice caps in particular, right? And that's leading to these warmer ocean temperatures. And then that releases the carbon dioxide. So this carbon dioxide is occurring in response to these initial things. Now, what happens later is that carbon dioxide has that positive feedback. So while it builds up, it has that greenhouse effect, and it lends and it accelerates this warming. But because of this, it's going to lag initially, or it's going to lag temperatures, right? Because it's not that initial driving factor. But what we're seeing now is the opposite, and it's because we are inputting carbon dioxide right here. So we're not seeing that lag right now. We're seeing increased levels of carbon dioxide and temperatures following along with it, right? So another thing that it goes against this natural cycle, that what we would expect more of a lag if this was related to natural drivers of climate change, and we're not seeing that now. We're seeing what is more in line with us emitting carbon dioxide and the temperature changing as a result. And really another, which kind of goes along with all of this, is there is that strong correlation between our emissions of greenhouse gases and rise in global temperature that you see here, right? And nothing else explains this better than greenhouse gases. Nothing else explains this rise in temperature better than that emission of greenhouse gases. We know their effect. We know the greenhouse effect is real. We know that greenhouse gases, carbon dioxide, methane, nitrous oxides, and those fluorinated compounds, we know they absorb infrared radiation and re-emit it back. We know we are emitting these gases at a higher level and creating concentrations higher than we've seen in the past 800,000 years. And we see a corresponding increase in temperature, right? So all this puts together, it's hard to argue against anything other than human impacts and human emissions driving our current climate change. So with that, I think I'll leave it there for this lecture. We will start up with the next lecture now, recognizing this, looking at what are the current impacts, future impacts, and what we can do to mitigate it in the future.